The universe has a sense of humor, and the James Webb Space Telescope is in on the joke. Just when scientists were getting an idea of how the universe began, Webb threw them a curveball. Its observations of the pillars of creation, where new stars are born, to the discovery of dark matter stars have shocked scientists all over the world. It seems that the more we learn about the universe, the more mysterious it becomes. When the JWST was launched on December 25, 2021, scientists didn't know what to expect from this massive telescope. But when the first images arrived in July 2022, shocked would be an understatement. The images were the clearest pictures of space that we had ever seen. With its unprecedented infrared capabilities, Webb was able to detect carbon dioxide in Europa's oceans and identify complex organic molecules in the first galaxies. But perhaps the most puzzling discovery was the existence of massive, mature galaxies only 500 to 700 million years after the Big Bang. This finding has sent shockwaves through the astronomical community, challenging long-held theories about galaxy formation and cosmic evolution. For decades, scientists believed that galaxies began as small clouds of gas and dust, gradually growing larger over billions of years. This view was supported by observations made with previous telescopes, including the Hubble Space Telescope. However, Webb discovered that these newly formed galaxies are as large as our own Milky Way, containing complex structures and mature stellar populations. This revelation has left astronomers scratching their heads, making us question everything we thought we knew about how galaxies formed in the early universe. According to previous models, significant galaxy formation was thought to begin only after 1 to 2 billion years after the Big Bang. Webb's observations suggest that this process began much earlier and proceeded far more rapidly than anyone anticipated. This accelerated timeline of galaxy formation raises fascinating questions about the conditions in the early universe. Were the first stars and galaxies forming much faster than previously believed? And could there have been unique cosmic conditions that allowed for such rapid growth, which we have yet to understand? In addition, the implications of these findings extend beyond just galaxy formation. Webb has also detected supermassive black holes in this early period, including one named Sears 1019, with a mass up to 10 million times that of our Sun. This black hole existed only 570 million years after the Big Bang, challenging our understanding that such black holes would take billions of years to form. Webb's findings suggest that the early universe was a far more complex and dynamic place than we have ever imagined. The existence of mature galaxies and supermassive black holes so soon after the Big Bang indicates that the conditions for rapid growth and evolution were present from the very beginning. But the JWST stumbled upon an even more fascinating phenomenon, one that could rewrite the story of the universe's first billion years. In July 2023, the James Webb Space Telescope identified 3 bright objects that might be dark stars powered by dark matter. Dark matter, the invisible substance that makes up approximately 85% of the universe's matter, has long been a subject of intense scientific debate. While its gravitational effects on visible matter are well documented, direct observation of dark matter has remained frustratingly out of reach. The potential discovery of dark stars, however, could provide an unprecedented window into the nature of this mysterious substance. Unlike conventional stars, which generate energy through nuclear fusion in their cores, dark stars would get their power from the destruction of dark matter particles. This process could potentially allow these objects to grow to enormous sizes, far surpassing the mass of typical stars. The implications of this discovery are incredible. If dark stars exist, they could help explain the presence of unexpectedly large galaxies in the early universe, a phenomenon that has puzzled astronomers since Webb first revealed these massive space objects. Moreover, the study of dark stars could provide a unique opportunity to probe the nature of dark matter itself. By observing how these hypothetical objects behave and evolve, scientists might gain crucial information about the properties of dark matter particles, potentially bringing us closer to solving one of the greatest mysteries in modern physics. In addition to its observations of the early universe, Webb's discoveries closer to home are equally as revolutionary. The telescope's unprecedented precision has opened a can of worms in the study of exoplanets, revealing worlds that expand our search for life beyond Earth. One of Webb's most intriguing finds is K2-18b, an exoplanet located approximately 120 light-years from our solar system. This celestial body belongs to a class of planets known as Hycean worlds, characterized by hydrogen-rich atmospheres and potentially ocean-covered surfaces. These attributes make them prime candidates in the quest for extraterrestrial life. Webb's analysis of K2-18b's atmosphere has produced remarkable results. The telescope detected significant amounts of methane and carbon dioxide, two gases that play crucial roles in Earth's biological processes. The abundance of methane and carbon dioxide, combined with low levels of ammonia, supports the hypothesis of a water ocean beneath the planet's hydrogen-rich atmosphere. But it's the potential presence of dimethyl sulfide, or DMS, that has truly captured scientists' attention. On our planet, DMS is produced exclusively by living organisms, particularly phytoplankton in marine environments. What makes these discoveries particularly remarkable is the efficiency with which Webb has obtained them. The findings regarding K2-18b were based on just 2 observations. Webb's advanced spectroscopic abilities allow it to analyze the chemical makeup of exoplanet atmospheres by examining light from host stars as it passes through these alien skies. This capability marks a significant advancement over previous telescopes, allowing scientists to study a wider range of potential habitats for extraterrestrial life. But if it can detect the atmospheric composition of planets hundreds of light-years away, just imagine what it can reveal about the planets and moons in our own solar system. Jupiter, the largest planet in our solar system, has long fascinated astronomers with its swirling storms and banded atmosphere. Yet, Webb's observations have revealed a feature that has avoided detection for centuries: a high-speed jet stream over 3,000 miles wide, traveling at about 320 miles per hour. This massive atmospheric current, invisible to previous instruments, raises interesting questions about the dynamics of gas giant atmospheres and how the layers of the planet's atmosphere actually interact with each other. But Jupiter's surprises don't end there. Webb's infrared sensors have looked through the icy crust of Europa, one of Jupiter's moons, to detect carbon dioxide in its subsurface oceans. This finding marks a significant milestone in our search for potentially habitable environments beyond Earth. The presence of carbon dioxide suggests complex chemical processes occurring beneath Europa's frozen surface, since this essential chemical is a universal building block for life as we know it. In addition, it also detected a surprisingly large water vapor plume erupting from Saturn's moon Enceladus. However, it is important to note that capturing images of planets with the James Webb Space Telescope is difficult because planets are very bright, which can overload the telescope's sensors even with quick snapshots. And unlike stars, planets are bigger and more spread out, making them harder to photograph. Additionally, planets spin quickly and move fast across the sky. But despite these challenges, early results show that the telescope can successfully study planets, proving its ability to observe them effectively. However, while the telescope captured images of the early universe and potential signs of life on exoplanets and moons, its most important contribution might be shedding light on the fundamental question: how fast is the universe really expanding? This cosmic problem, known as the Hubble tension, has puzzled astronomers for years. The JWST was expected to provide clarity. Instead, it has deepened the mystery. The expansion rate of the universe, described by the Hubble constant, is a cornerstone of modern cosmology. It tells us how quickly galaxies are moving away from each other due to the expansion of space itself. For decades, astronomers have used various methods to measure this rate, but different techniques have yielded conflicting results. On one side of the debate, we have measurements from the early universe. The European Space Agency's Planck spacecraft, which studied the cosmic microwave background radiation left over from the Big Bang, suggests a Hubble constant of about 67 kilometers per second per megaparsec. This means that for every megaparsec, or 3.26 million light-years of distance, the expansion adds about 67 kilometers per second to a galaxy's velocity away from us. On the other side, measurements from the Hubble Space Telescope, which used Cepheid variable stars in Type 1a supernova, found a higher value of about 73 kilometers per second per megaparsec. Enter the James Webb Space Telescope. With its ability to explore deeper into space and time than ever before, astronomers hoped it would resolve the Hubble tension. Webb's observations of Cepheid variable stars, crucial for measuring cosmic distances, were eagerly anticipated. These stars pulsate regularly, with their brightness linked to their period, making them valuable for measuring distances in the universe. In other words, these stars brighten and dim regularly, and by comparing their true brightness to how they appear from Earth, scientists can measure their distance in the universe. However, Webb's findings have not resolved the tension. Instead, they've confirmed the higher expansion rate of about 74 kilometers per second per megaparsec, aligning with the Hubble Space Telescope's measurements. This disagreement between our most advanced instruments and techniques shows a fundamental gap in our understanding of the universe. If the universe is expanding faster than our models predict, it could mean that our theories about dark energy, dark matter, or even the fundamental laws of physics need revision. If the higher expansion rate is correct, it could imply that the universe is younger than we thought, or that it has evolved differently than our current models predict. In the quest to understand our universe, each discovery brings new questions. The James Webb Space Telescope has already reshaped our understanding of the universe in 2 years, from detecting complex organic molecules in ancient galaxies to discovering potential dark stars powered by dark matter. But its journey is far from over. What other secrets might it uncover in the coming years? Could Webb detect biosignatures on distant exoplanets, providing the first evidence of extraterrestrial life? Might it reveal the nature of dark matter or shed light on the universe's accelerating expansion? The future of universal exploration with Webb promises to be as exciting as it is unpredictable, potentially answering fundamental questions about our place in the universe.